Now we're going parallel for our graph matching algorithm, and we need a partitioning of the data for that. In this case, a partitioning of the vertices. A p-way vertex partitioning is a splitting of the vertex set V into sets V0 up to Vp minus 1, such that the union equals V and that all the sets are mutually disjoint. And then Vs is the local vertex set of processor Ps. We store then the vertex V and its adjacency set together on processor P of phi V. Phi is the mapping that maps vertices to processor numbers. And then this adjacency set V may contain vertices or edges that are on another processor. These vertices we call halo vertices. And the halo of a processor is the set of surrounding data that are needed and that interact directly with the processor, causing communication. In this case, the halo set of S is the union of all the adjacency lists of the vertices in Vs, excluding Vs itself. And if you have a good partitioning, the size of the halo set is a lot smaller than the size of the set Vs itself. The halo set of this partitioned graph consists of a number of vertices, and my question to you, what is the halo set of the red processor? Here you see the answer. The halo set consists of two blue vertices, and they are encircled by a red circle. So these are vertices that are remote, that are not on the red processor, but that are needed by the red processor. And the red processor owns the four red vertices, and the edge set of this processor is the set ES, which is defined as all edges UV, where V is in the vertex set. And this edge set for the red processor consists of six edges, 4 internal edges, which are shown completely red, and 2 external, also called cut edges, which are shown in red and blue. So, having the data distributed, we can parallelize our local domination algorithm, and this is the main loop. We start with an empty local matching set, MS. We also have a full Q. QS is the complete local vertex set VS. And we have something new. We have a queue of received messages, RS. And that's a set that contains all the messages that we received in the current superset, superstep. Then the main loop runs on while we're not done. We start, of course, with done equals false. And then, how do we detect that we are done? Well, every processor has a local variable, done of S, which is that both the received messages, Q is empty, and the work queue, QS, is empty. If you receive messages, you may have to do work, but if you didn't receive anything, that doesn't cause any work, and if the work queue, QS, is empty as well, then you are done. But if you are done and others are not, then we're not done. And so what we do is we put the information, the local information done S, into all the processors, And then after the next synchronization, which you see with the sync at the bottom, then everybody can compute the AND of all the dones. If all are done, then this single variable done is also true, and we stop. So this is the framework that helps detecting termination of the algorithm. So what happens in the algorithm? Basically, two things. First, we process the received messages. Details will be given later. And then we pick vertices from our queue until we are done with that, until the queue is empty. And, well, you know how to fill in the dots, because we've seen that in the sequential algorithm. Now, the sequential algorithm we've shown before, but a few things are added. So let's go through this. So first you pick a vertex, remove it from the queue, you find its preference, you set the preference to u, and then we're going to look whether the preference is mutual. So if I see that u is the suitor of v, then we have a match. Because the preference is mutual, we registered it in the local set ms, and we set locally, we set the degree to 0, because v is a local vertex, so we can set its degree to 0. But then we have a match to u, then u could be local or non-local. So if u is local, if it is in the vertex set vs, then we also set the degree of u to 0. But otherwise we have to do something remote. We put a message called accept of v to u, v accepts u, in the owner of u, and that's processor phi u. Now if u is not the suitor of v, then we have to, in the case that it is local, we already could prevent that, because in the find preferences we will only look at suitors, because those have a chance. But for the non-local case, u could be not residing on processor S, then we send a proposal to the owner of u. So that's how we insert communication into this algorithm. So how should you propose? Well, one of the partners has to go down on their knees, on their knee, and that is what is being done. And in our formal algorithm, propose VU means V proposes to U. How should you not propose? This is something that happened in the Netherlands in 2014, where someone was very enthusiastic and proposed to his girlfriend in this way, but then the truck moved over and and hit the house. No one got hurt. They ran off to Paris, and I assume they had a good time. This is in the case of accept, she accepted. Accept VU means V accepts U. So we can put these proposals and accepts in our algorithm. They create communication, and the strong point of BSP is that you can put it anywhere in your algorithm. You can write it, and so you can mix computation and communication, and still the communication is separated from the computation at the sync. First all the computations happen, and only then the communications are carried out. And that means that we also can reason about this. We can still assume the superstep structure, and that helps us in thinking in sync. Here you see what rejecting a suitor entails. So I've written a function here, reject suitor, And what it does is it rejects, V rejects a suitor X. And in this case, you check whether X is not nil. It's a true loser in this case. And if it is local, X is in the local set Vs, then you just have to add it to the work queue and set its preference to nil. Otherwise, you have to put a message, a reject message, into the processor, the owner of X. So reject VU means V rejects U. Then we have seen the whole part of picking vertices and putting them in, picking them from the queue, etc. But we didn't discuss yet the processing of the received messages. Well, it's very simple. You pick messages one by one from the queue RS, from RS, remove it from RS, and then you have to do something based on what type of message it is. It's a proposal, an accept, or a sad reject. Now, if you have received a proposal, if U is the preference of V, the one who proposes to you is your preference, then you have a match. Now it is imperative that you remember to whom you proposed, because only that way we can detect that there is a match. You may get an answer from a remote processor a little bit later. And that means that in the parallel algorithm, we need to store both the preference and the suitor of a vertex. Now, why is this superstep structure important? Because you can reason using this. So let's assume that U proposes to V, and V has proposed already to U, and we detect this by U equals the preference of V. If this is the situation, this means that both must have proposed at the same time. And actually, because of the superstep structure, it also means that both can detect it at the same time, and they can tacitly accept. They need not send an accept message to each other, because they both know. Now, this needs a proof. And why is that? Let's assume that you receive a proposal. You proposed to V, so it sent it in the previous superstep. But you have set your preference to V previously. Now, if you would have, and setting your preference means you have proposed to U already. Now, let's assume that you have proposed already, not in the previous superstep, but before that. Then in that case, in the previous superstep, or an earlier superstep, the owner of U will have received your message and will answer you appropriately, either by sending a reject, but in this case, of course, it didn't happen. It would send an accept to you. So because of that, you didn't receive an accept, you received a proposal. And that means that the other side did not know yet about your proposal. And because of that, we know that they crossed each other. They both sent a proposal at the same time. Let's summarize what we have learned in this video. We parallelized the algorithm by partitioning the set V into subsets Vs. Every processor PS then has such a subset, Vs, and it also has a halo set, which consists of all the vertices that surround the vertex, vertex set Vs, so are connected to it, but the vertices are not inside Vs. And we then have an edge set, which are all the connections both internal and external. And then we have a parallel algorithm based on mixed supersteps, where we initiate communication from anywhere where we want it, and that's really a nice property for BSP. And then we still have the superstep structure. And every step of the algorithm starts with processing received messages, and then setting preferences, and after that sending out new messages. Final question. I already showed a little bit of what you have to do when you receive a proposal. For example, what happens if there is a match. But if not, you have to fill in the dots, formulate the remainder of the processing of a received proposal. And what has to happen then is that you get a proposal, you have to compare it to the weight of the suitor at the moment, and then you reject the appropriate vertex. All in the formulation as we see.